Okay, so we have a Taylor series, the definition for a Taylor series here. I do want you to remember that we already defined Taylor polynomials of order n, all right? This is super similar. All right, so suppose a function f has derivatives of all orders. See, when we define a Taylor polynomial, earlier in a previous lesson, we said f has derivatives of orders all the way up to n. But now we're saying of all orders on an interval centered at a point a. So a is your the center of the series. So the Taylor series for f centered at a is f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a quantity squared plus f triple prime of a over 3 factorial times x minus a quantity cubed plus etc. But notice that we don't stop at order at the nth derivative. We keep going indefinitely. So really a Taylor series is a Taylor polynomial extended, or a Taylor polynomial where we allow n, the nth order, right, to extend indefinitely. Basically, you're letting n go to infinity. So a Taylor series will go from k equal to 0, not to n, but to infinity. So this is just a natural extension of a Taylor polynomial. Okay, these are your coefficients. The kth derivative of f evaluated at a over k factorial, and then x minus a to the power of k. Again, a is your center. Now, this is important. If the Taylor series is centered at 0, so if a is 0, then that Taylor series is called a Maclaurin series. A Maclaurin series is simply a Taylor series that is centered at 0. All right, here's our first example. We're going to find a Maclaurin series for this function. Again, don't forget, a Maclaurin series just means we're finding a Taylor series centered at 0. All right, also what we'll do once we find the Maclaurin series is we'll find the interval of convergence for that series. Okay, here we go. So what we need to do first is we need to find all the derivatives, okay? And then evaluate all the derivatives, including the original function, at 0. All right, so let's go for it now. All right, so if f is cosine, that means f of 0 is cosine of 0, which is 1. All right, f prime of x is negative sine of x. Oops, make that a little, there we go. This implies that f prime at 0, which is your center, right, is 0. F double prime is equal to negative cosine of x. That means f double prime centered at 0 is negative 1. Okay, and then now we have f triple prime. F triple prime is equal to sine of x. That implies that f triple prime at 0 is equal to 0. And f quadruple prime, no, we don't say that. The fourth derivative of f is equal to cosine of x. And this is the original function that we started with. And this fourth derivative of f evaluated at 0 is 1. And what I'm going to do is I'm going to stop here and I'm going to say etc. because we've noticed a pattern. Okay, notice that the pattern is that every odd order derivative, like the first derivative, the third derivative, and so forth, is equal to 0. Okay, so basically when k is odd, then we just get 0. All right. So I think we can start building this Maclaurin series. All right, so it starts with 1, right? That 1 right there is coming from right here, the function, the original function evaluated at your center, 0, is 1. All right, so that's where that's coming from. Now, my next term, my first degree, f prime, this term I will not even write. Why not? Because its coefficient is 0, so it completely wipes out that term. So I'll jump to the second derivative. The coefficient is negative. Okay, negative 1 over 2 factorial, which is just 2. So there's the coefficient, and then we have x squared. Technically, x minus 0, which is the center, squared. We could have just written x squared, right? And then the third derivative, again, is 0, so I won't even bother writing it because the coefficient is 0 there. Wipes out that term entirely. So now I'm here. The coefficient here is 1 positive, and it's positive 1 over 4 factorial, right? Remember, we skipped over 3 factorial because the third derivative of f at 0 is 0. All right, so now I'm at the 4 factorial. X minus 0 raised to the 4th power. You know what I mean? And then the fifth, the fifth order coefficient will be 0 again, so that's wiped out. So I'm jumping to the 6th order. So then it will be well, we can look at our pattern, right? So positive, negative, positive, negative. So then this should be a negative. Let me erase that. Minus, right? Because these coefficients repeat in a pattern, you know what I mean? And so then we have minus, and then 1 over 6 factorial, x minus 0 raised to the 6th power. So I guess I can make this nicer and more concise, right? So the Maclaurin series is, here, let me change the color for us. The Maclaurin series is 1 minus x squared over 2 plus x to the 4th power over 4 factorial minus x to the 6th power over 6 factorial, plus etc. That's really cool, everybody, that this is the Maclaurin series, which is a Taylor series centered at 0 for the cosine function. We can use summation notation. All right, so notice that the signs are alternating, so you know you're going to need this in your little formula, right? -1 raised to the power of k. And notice that all of your denominators are factorials, including this one. This is 2 factorial, but they're only even numbered factorials, right? 3 factorials not there, 5 factorials not there. So even numbers are of this form, 2k, those are even numbers, factorial. That's giving you all of your coefficients. And then it's x, for the variable parts, it's x raised to even powers only. So x to the power of 2k as k goes from 0 to infinity. So then this is the summation notation for this series, which represents the cosine function. Awesome. If you notice, this series only contains even powers for the variables. Only even powers. The 0th power, the 2nd degree, the 4th degree, 6th degree, which kind of reflects the fact that the cosine function is an even function. Remember, out of all your trig functions, cosine is the only even function. Well, cosine and its reciprocal secant, they're even. But all the others are odd. So cosine is an even function. And this series only contains even-powered variables. That's really, really interesting. Now, now that we have the Maclaurin series, what's the interval of convergence? Well, for what values of x does the series converge? Let's use the ratio test. We're using the ratio test on the series. Okay, here's my ratio test. It looks really complicated, but let's simplify. Be careful here. Let me scroll back up here. Be careful here. You're letting k be k plus 1, right, for the ratio test. But it's 2 times k plus 1. So just be careful with your grouping symbols. It's not 2 times k and then plus 1. No, it's 2 times k plus 1. So that's a huge difference. Here as well, it's not 2k plus 1 factorial. It's not this. It's not this. That would get you, lead you in the wrong direction. That's not what it is. Instead, it is 2 times k plus 1 factorial, okay? So, which turns out to be something different. All right, so just be careful on how you write it. All right, so I'm going to try my best to simplify here. So bear with me. Let me move this up. So then this is equal to the limit as k goes to infinity. Okay, here we go. So I get x to the power of 2k plus 2. Let's see, over 2k plus 2. Gosh, that's sloppy. I'm so sorry. That's a 2 right there. Okay, 2k plus 2 factorial times 2k factorial over x to the 2k. Technically, we need absolute values around some of this. So let me just keep absolute value bars right there, and then I'll simplify without any absolute values. Okay, so let's see. We have x to the power of 2k plus 2, and then we have x to the power of 2k in the denominator. So let's recall that, the quotient rule for exponents says that we can simplify these variable expressions by taking this power, 2k plus 2, subtracting that power. But 2k plus 2 minus 2k just leaves you with 2, x squared, that is. So this is just x squared. There. I don't need absolute value bars around that because that's always positive. I don't know why I changed to writing in red. Oh well, it is what it is. And then 2k factorial divided by 2k plus 2 factorial, that just leaves you with 1 over 2k, let's see, plus 1 times 2k plus 2, like that. Okay, let me move this 1 like that. Okay, folks, so what is this equal to? Well, since the numerator is fixed and k is going to infinity, the only, this limit rather, is equal to 0. Regardless of what you choose for x, this is 0, which means no matter what that is, times 0, this is all equal to 0. The limit is equal to 0. Now, by the ratio test, because this value, 0, is less than 1, we know that this series converges absolutely for all x. So my interval of convergence is all real numbers. All right, cool. Let's look at another one. All right, we have this rational function, f of x is equal to 1 over 1 minus x. Remember that we're looking for a Maclaurin series, so the center is equal to 0. All right, so I need to find like my all of my derivatives, and I need to evaluate all those derivatives at 0. But let's start with this one first. Okay, this is the given function. So f of 0 is equal to 1. F prime. If you use the quotient rule to differentiate here, or do the power rule, you'll find that the derivative is equal to 1 over 1 minus x squared. Oops, sorry, I wrote that wrong. Hold on. There we go. 1 minus x quantity squared. Anyway, so f prime evaluated at 0 is equal to 1. Okay, f double prime now. Again, use the power rule. Probably would be the best way to do it. Of course, that means rewriting this as 1 minus x raised to the power of negative 2, and then you can use the power rule to differentiate. But anyway, f double prime is going to be 2 over 1 minus x quantity cubed. That implies that f double prime at 0 is equal to 2. F triple prime, make sure that looks like a triple prime there. F triple prime will be equal to 6 over 1 minus x to the 4th power. I hope you're seeing a pattern here. So then f triple prime at 0 is equal to 6. Notice this number matches that number. Notice this number matches that one. Also notice that 6 is equal to, what is this, triple prime? So this is the third derivative. 6 is equal to 3 factorial. 6 is equal to 3 factorial. 2 is equal to 2 factorial. Just something to think about. Let's go one more. So then f, the fourth derivative of f is equal to 24 over 1 minus x raised to the power of 5, which implies that f, the fourth derivative of f, evaluated at 0 is equal to 24. So I think you see the pattern here. Notice that 24 is 4 factorial. Here, let me write that down. 4 factorial is equal to 4 times 3 times 2 times 1. That's equal to 24. 24 is 4 factorial. 24, this numerator is just 4 factorial. This numerator is just 3 factorial, right? So really, what we can do is watch what I do here, folks. This numerator here, instead of writing it at 6, instead of writing that number as 6, watch this. Maybe the pattern would be more evident if I wrote that instead of at 6, 3 factorial. 3 factorial instead of 6. Just so that I can see the pattern. So instead of 24, what if I wrote this as 4 factorial? Then I think the pattern is more evident. And don't forget that 2 is equivalent to 2 factorial, so that really is a factorial as well. So I think we can get our Maclaurin series then. We see the pattern, you know what I mean? We see the pattern. So let's get our Maclaurin series now. Okay, it is 1, the very first coefficient, f of 0, right, is 1, plus the first coefficient, the first degree, I'm looking right here, is 1, right? Let me write it out the way it's really. Here, let me start over here, folks, okay? Bear with me. So the Maclaurin series, which is a Taylor series centered at 0, is f of 0, right? That's 1, plus. And then it is f prime of 0 times x minus 0, right? Plus f double prime of 0 over 2 factorial x minus 0 quantity squared. So, and then plus, etc., right? We know how to build that. Anyway, that's the reason why I started with the number 1, because f of 0 is 1. Okay. And then f prime of 0, you can look up here. There it is. F prime of 0 is 1. So I'm going to use that here. So then this is just 1 times x. So it's just x plus. And then f prime of f double prime, excuse me, of 0 is 2 factorial over 2 factorial. Wait, f double prime of 0 is 2 factorial over 2 factorial. That's just equal to 1. So then this is just 1 times x squared plus, oh my gosh, f triple prime, look at this. F triple prime of 0 is 3 factorial over 3 factorial would be the next denominator. So that's equal to 1 times x cubed. So I hope you see the pattern here. Let's just continue then. X cubed plus x to the fourth and so forth plus etc. Of course, this can be written in summation notation as just x to the power k, as k goes from 0 to infinity. This is the Maclaurin series for that rational function, 1 over 1 minus x. All right, so now I think what's important is for us to find the interval of convergence. But this power series, we've looked at it before, right? So we already did this in an earlier lesson. You can confirm that we already found that the interval of convergence is the absolute value of x less than 1. You know, what's really important is this series, this Taylor series, is a Taylor series for this function, everybody. Watch this. Oops, I wrote it wrong. For this function, okay? This is an important point. This Maclaurin series is the Maclaurin series that represents this function, but only on this interval, okay? Now, if we want this function, but on a different interval, right? So if we have a different interval, then that means we need a new center, okay? And the series could be different, okay? The series can be different. So my point is, this Maclaurin series is the series. It's unique. It is the one and only series that represents this function, but it represents this function centered at 0 on this interval. If you look at a different interval, a different center, then it's a different series. Here, for example, look at this. So now we're finding a Taylor series for the same function, but now it's centered at 5. Folks, because the center is not 0, we cannot call it a Maclaurin series. It's a Taylor series. All right. Notice that it being centered at 5 changes things. All right. All right. So we already found a lot of information from earlier, so we can use it. I'm talking about this information up here, folks. Let me see if I can scroll and show you. Yeah, here it is. Look at the pattern of the derivatives. Okay, we don't need to do this part over again, okay, because we already did it. Look at the pattern of the derivatives. So it's 1 over 1 minus x, right, to the first power. The first derivative is 1 over 1 minus x quantity squared, and then 2 factorial over 1 minus x cubed, 3 factorial, 1 minus x to the fourth power. And so forth. Notice that when this is being raised to the fourth power, this here is 4 is 1 more than 3. You know what I mean? 4 is 1 more than 3. So this is the third derivative. So it's 3 factorial over 1 more than 3 as the power. Same thing here. This is the fourth derivative, so the numerator is 4 factorial, but the power is 1 more than the number 4. All right, so I think we should use that pattern. I don't want us to work, harder than we need to, okay? So we know that all of the derivatives will be of this form. If you are finding the kth derivative, of course, centered at 5, right? Evaluated at 5. Oops, I didn't mean to write that. The kth derivative evaluated at actually, let's make this, sorry, hold on. Let's make this x, and then we'll plug in 5 after. So when you're finding the kth derivative of your function, we know that since it's the kth derivative, the numerator, you saw the pattern, the numerator is k factorial, and the denominator is 1 minus x raised to the power of 1 more than that number, 1 more than k, so k plus 1. These are all of the derivatives, okay? The derivative functions, okay? Now, what about the coefficients? We call the coefficients c sub k, okay? These are all the coefficients. They are the kth derivative, evaluated at 5, these are the coefficients, all over k factorial, okay? Which always turned out to be, all of these coefficients turned out to be k factorial over k factorial times 1 minus 5 to the power of k plus 1. Basically, all we did here was plug 5 into, we just evaluated this, right? The kth derivative at 5. So we're actually just plugging 5 in for x. So it's k factorial over 1 minus 5, right there, 1 minus 5 to the power of k plus 1. But let's not forget that the coefficients have a k factorial in the denominator as well, okay? All right, so then I think we're ready to write down the Taylor series, but this time it's evaluated or not evaluated, but this time it is centered at 5. And notice that this can be simplified, of course. K factorial divides out with k factorial, and 1 minus 5 is negative 4. So then this is really 1 over, oops, I didn't want to start writing in red. 1 over negative 4 raised to the power of k plus 1. Okay, I think we're ready. Let's write it out, folks. Okay, so here we go. The Maclaurin series. It'll be the summation of. Okay. This negative right here is going to make your signs alternate. Whether or not k plus 1, the power is even or odd, will make this positive, negative, positive, negative. So I can write that negative as a negative 1 raised to the power of k plus 1. And that way, my denominator is simply 4 raised to the power of k plus 1. Okay, that's a nicer way of writing that. Okay, and then your center is at 5. So it's x minus 5 to the power of k. So here's your Maclaurin series. I'm sorry, your Taylor series, not Maclaurin, right? Not Maclaurin. If I said that earlier, sorry about that. It's not a Maclaurin series because it's not centered at 0, right? It's a Taylor series. So this is our Taylor series for that same function, but centered at 5. We can list out a few of the terms. I think that'd be cool if we did that. So then this is equal to, and I forgot my index here. So k is 0 to infinity. Let's plug in 0. So anything raised to the 0th power is 1. So that's 1. And then this would end up being negative, and 4 to the first power. So then the very first term is negative 1/4. Now let's plug in k equal to 1. When k is 1, this is 1 plus 1, which is 2. Negative 1 squared is positive 1. This is going to be x minus 5 raised to the first power, which is just x minus 5. So that's your numerator. And when k is 1, this ends up being 4 squared. All right, cool. When you let k be 2, this is 2 plus 1, which is odd. So this is going to be a negative term. The next term is negative. And then you're going to have x minus 5. Remember, k is 2, so this is x minus 5 quantity squared all over 4 cubed. And I think you see the pattern here. So we can keep going and just calling out the pattern. X minus 5 quantity cubed over 4 to the 4th power. That term right there was positive. The next one would be negative, etc. Let's find the interval of convergence. All right, I'm using the ratio test here to find my interval of convergence. All right, so it's time to simplify. So then this is equal to the limit as k goes to infinity. And let's see what we have here. You know, the absolute value makes these go away, these -1 expressions. And then x minus 5 raised to the power of k plus 1 will divide out with x minus 5 raised to the power of just k and leave you with just one copy of x minus 5. I still have absolute value bars around that. And then in the denominator, 4 raised to the power of k plus 1 will divide out with 4 to the power of k plus 2 and leave you with just one copy of 4 like that. So that's how that simplifies. And the thing is, you and I know that, first of all, no more k's at all. So then this is the limit. This is what this is equal to. Anyway, we know that the power series converges absolutely only when this is less than 1. So it converges absolutely only when the absolute value of x minus 5 over 4 is less than 1. That's equivalent to saying that -1 is less than x minus 5 over 4, which is less than 1, which is -4 is less than x minus 5, which is less than 4. I multiplied by 4, and adding 5 gives me my interval of convergence being between 1 and 9. Between 1 and 9. So my interval of convergence is 1 to 9. Now, let's not forget that your center is 5. So a little picture here if it helps. So if this is 5, this is your center, right? That's why it's not a Maclaurin series, because the center is not 0. But anyway, here's 1, and here is 9. So therefore, this is your interval of convergence, which means that R, capital R, which is your radius of convergence, is equal to 4. This is also 4 right here. Okay. What you might want to do is plug in 1 and plug in 9 into your power series to confirm that the series actually diverges at these endpoints. So these endpoints are not included. Again, I invite you to plug 1 in, plug 9 into the series to confirm that.